Okay, so last time let me just remind you, of course, no class next week. I assume you don't need me to tell you that, but always helps to be on the same page about that. Okay, last time we were talking about the interaction between open and closed embeddings. In particular, we had defined a locally closed embedding. To be, I have an X. I look at a closed embedding into some Z, and then I compose that with an open embedding into some Y. Now, in topology, locally closed usually means the intersection of an open set and a closed set. And if I have an intersection of, so if I have U open and C closed, then indeed I can look at their intersection and I can either think of that as having an open embedding into C and then a closed embedding into Y, or I can think of that as a closed embedding into U and an open embedding into Y. So this is in topological spaces. Any topological space. Yeah. And you can check that in topological spaces, being a closed embedding and then an open embedding is equivalent to this. And what's the proof? The proof is, well, I take U to be my Z, and I take C to be the closure of X. So if I was trying to use this argument in schemes, I would need to know what it meant to take this guy and take its closure. So this sort of naturally leads us to the question, what is the closure of, well, it's tempting to say a subscheme, but we've only defined open subschemes and closed subschemes. So I don't want to try to define a more general notion of subscheme than this. So, but if I had any other notion, it would have to involve a morphism from that subscheme into your scheme. So the sort of general kind of framework we already have where we can think about this question is, what is the closure of the image of a map of schemes? Right. That's what I sort of would need to make this argument from topological spaces work in this world. And of course, it's just a natural question, right? So the result should be, well, I know what the image is as a subset, and I know what it means to take the closure of that in my topological space. So my hope is that I get a scheme structure on the closure of the image as a topological space. And the short answer is, oh, not quite if your map is really bad. So if your map isn't too bad, then everything will work very nicely, but you need some extra conditions. Yes.
Do you want
Well, What I mean is, um, so obviously any answer to this question should be a closed subscheme. And I remember that being a closed subscheme is more information than just being a closed subset of the topological space. It's that and the information of what the scheme structure is. Yes. So if I give you a map, is there one correct one to put on the closure of the image? Right? That's why this is a subtle notion. That I can't just take the closure as the topological space, because I don't immediately know a scheme structure on that. And if I just chose one, it might kind of interact badly with the map. All right. I'm kind of repeating stuff from last time because I had gotten this far. The sort of natural way to do this is, well, the closure of a set, I intersect all the closed sets containing it. So now when I want a closed subscheme structure, I want to intersect all the closed subschemes containing. So what we do, so let's define a map from X to Y, right? And what is it going to mean that a closed subscheme contains the image of this map? It's just going to be that the map factors through the closed subscheme. So I have this factorization, as we were discussing last time, if and only if, well, any function f in O of y on some subset u, such that when I pull back this function, I get 0, is already 0. Z. So this is saying that when I take the ideal sheaf for Z, that's going to be contained in the kernel of B sharp. And I think basically the last thing I said in class last time is, well, it's tempting to try to use this to define the closure. So tempting to say that the image of the closure is just the vanishing scheme of this kernel. But I have to be a little bit careful about that, because if I want to define a subscheme, I have to take a quasi-coherent sheaf here. And I don't know that this kernel is quasi-coherent. So instead, I should take the closure of my image to be the vanishing set of the biggest quasi-coherent subsheaf. All right, and the kind of thing you should worry about is that, Vakil talks quite a bit about this example, so I'm just going to go through it very quickly. I can take A1, right? And then I can take mapping onto this, the union, not you, the union of spec of, so this is A1. I can take it over C. There's nothing important about C here. The spec of C of T mod t to the n for all n. So I have an infinite number of points here, and each one is a little bit thicker than the one before. So if you think about the sheaf of the kernel here, it's real weird. Because if I look at the whole open set, there's nothing in the kernel, right? Or any open set containing the origin. Being in the kernel of the pullback would mean that I vanish to infinite order at the origin. So there are no rational functions that are defined at the origin that satisfy that property. But of course, if I remove the origin, everything pulls back to zero. All right. So what's the closure of this image? Well, there's only one conceivable answer. It's the whole thing, right? Right. A subscheme of this guy is defined by an ideal. And I see immediately, oh, the ideal of global functions that pull back to zero is trivial. So you have to be really careful about this closure operation. And, of course, the answer is ultimately there should be something that isn't quite a closed subscheme. That's the closure of this image, right? I should take kind of a very thick neighborhood around this guy, but that's not a subscheme. It's sort of there's a formal subscheme that's much better. Yeah. Can you sure. So if I have two closed subschemes, x1, x2, right? One way I could say this is x1 is contained in x2 if the inclusion of x1 into y factors through x2. Now let's think about that in terms of ideals, right? How do I get inclusions of the subspaces corresponding to ideals? Well, exactly what this means is there's an ideal sheaf, which is all the functions on y that pull back to zero on x2, right? And since this inclusion factors through here, those had better pull back to zero on x1 as well. So if I look at the ideal sheaves, I'm going to have this inclusion. So in general, this is sort of an important point. What does it mean to intersect two closed subschemes? This corresponds to taking the sum of their ideal sheaves, right? Just as when I intersect the zero sets of two ideals, I get the vanishing set of the sum of those ideals. And of course, this is the biggest closed subscheme that factors through both of these guys, right? I've got to have these guys. So we haven't talked about fibered product yet, in part because we've spent so long on closed subschemes, but right, this guy has a universal property. It's the universal thing that both maps through here and maps through here. So we'll be able to think about this in a moment as a fibered product. Yeah. Of the kernel. Right. So exactly what's happening here is I'm saying that a closed subscheme factors through here if and only if the ideal sheaf is contained in the kernel. So when I intersect all of those guys, what am I doing? I'm taking the direct sum of all the quasi-coherent ideal sheaves that lie in this kernel. when I take a sum of infinitely many quasi-coherent things, I still get something quasi-coherent, right? Because I don't have any like finitely generatedness hypotheses. I'm just saying like it sort of corresponds to a module. Um, I mean, I think it's sort of that's probably fancier than you need to think about it, right? There's an inclusion functor from quasi-coherent O modules to all O modules, and there's a right adjoint to that inclusion, which is take any O module and replace it with its largest quasi-coherent subsheaf. The sum, yeah. Well, right. I mean, this is sort of, this is something about how you think about right adjoints as I mean, what do I want to say here? Um, right. Taking, I'm looking at all maps of quasi-coherent sheaves into this guy, and I'm trying to construct the biggest one. But you can concretely think of that as just if I have two quasi-coherent subsheaves, or if I have an infinite number of quasi-coherent subsheaves, their sum is still a quasi-coherent subsheaf. But the point is it's not filtered. There isn't any natural partial order on them other than inclusion. Yeah. Yeah. It's just zero. Yeah, exactly. Exactly. Yeah, I mean, this is saying if I have a closed subsheaf that this map factors through, it has to be the whole thing. There aren't any proper closed subsheaves that this factors through because this guy always gets thick enough, right? That if I had any closed subsheaf, well, like it would only include things that vanish to some order here, and eventually I would have a problem. Right. Just yeah, this is one of these things that it's like, oh no, I realize now I should have carefully checked whether that was what was going on here. I mean, this shows you that it's bad, right? Um, and I don't want to absolutely swear that the issue here is that the kernel isn't quasi-coherent. I would want to check that. But it might be. I mean, certainly the kernel is kind of weird, right? Like it's because it's zero when you include this point and it's non-zero if you don't. So I think it might not be quasi-coherent because it's telling you like when you remove the origin, you don't just take the sections you had before you remove the origin and localize them, right? Like, yes. So I think this is a case where the kernel is not quasi-coherent. Right. And the point is, if it were quasi-coherent, if I took the kernel of C# on A1 minus the origin, right, then that would have to be the kernel phi on A1 localized with respect to the element T, right? And this is zero, this is not zero. Okay, good. So it's not quasi-coherent. Cool. Do. All right, so exactly what this is telling you is if I think about the image of this map as a map of topological spaces, the image is just this point. But if I look at the closure of the image as a map of schemes, the smallest closed subscheme that contains the image is the whole affine line. So I see here, this doesn't work in general, but theorem, if B is quasi-compact, or X is reduced, then you're okay. So somehow this is really the only problem, that you can have kind of infinitely many components and kind of keep requiring things to vanish to a higher and higher order. This is kind of telling you that's the only problem. I need infinitely many open subsets covering my pre-image, and I need to have some nilpotents that I can kind of make worse and worse and worse. Then the closure of this image as a subscheme. So we would often call this the scheme theoretic closure. Closure is a subscheme structure on the topological closure. Yeah. So one important special case of this is that, oh yeah. Well, I mean, this closure is defined as a subscheme of Y, right? It's which one? Subscheme is. Yeah, I mean, it's the point. I told you what the ideal sheaf is. So it's the points where the ideal, everything in the ideal sheaf vanishes. Now, what this is, right? This theorem tells you you have to put in some hypothesis, but once you do that hypothesis, then it's also the actual closure as a topological space. All right, so there's one sort of important special case of this where, I mean, it's just very upsetting that you have to make these choices to define a subscheme structure. So obviously there should be some kind of best subscheme structure. And of course we have a hint of how to do this, because if we have a Zariski closed subset, well, there are many ideals that correspond to it, but there's one kind of best choice, which is the radical, right? So every Zariski closed set has a unique reduced scheme structure. Which is basically just, well, the ideal sheaf for X and Y, I have to somehow define this purely in terms of the actual points of the closed set. We call this X red. So this means the ideal, this is all of the functions and O of Y on U, and I should tell you what this is on an open subset U, such that F is in the maximal ideal of Y T for all P in X intersect U. So this is basically define, right? We can define the radical as the intersection of all the prime ideals containing my my ideal. And so, right, a radical ideal is exactly one. Yes, sorry. Right, the radical of an ideal is exactly that. I take all of the primes, and I'm writing this in sort of the geometric way, right? The primes that correspond to points in the vanishing set of I, and I take the intersection of all of those prime ideals. But that's what this is. This is sort of a schemey way of saying that. So in particular, if U is affine, this is literally just taking the unique radical ideal that corresponds to the closed subset. Let me actually write this. If Y is affine, this is the subscheme structure. So Y is the spec of A. Given a closed subset, Zariski closed subset X, this is equal to V of I for a unique radical ideal. And this reduced scheme structure is just I take spec of A mod I for that radical ideal. You'll sometimes hear this called, this is sort of a ridiculous name, but it's the induced reduced scheme structure. And Bakil points out there's sort of a funny way of thinking about this, where given a closed subset, or actually any subset of the points of my scheme, I can let X set be X with the discrete topology such that if I look at the functions on a point P, I just define that to be the residue field where I take the local ring and mod out by its maximal ideal. So this is slightly insane. This is sort of, I completely kind of pull apart all the points of my scheme. But since I need a scheme structure, what I do is I think of every point as spec of this field, and then I take their disjoint union. I always have a map of X set into Y. And if I take the scheme theoretic closure of this image, then I'll get this reduced scheme structure. So scheme theoretic. Closure of image. Y gives the reduced scheme structure on the closure of X as a topological space. So this is a slightly crazy way to think about it, but if you sort of unravel all the definitions, it's just saying the same thing, right? If a function pulls back to 0 on here, that's just saying that when I take its stock, it lives in the maximal ideal at every point. So it vanishes at that point. Yes. Well, I just gave you a unique, I mean, oh, in the sense that there isn't any other reduced subscheme structure. Well, if I had a reduced subscheme structure, its ideal sheaf would have to contain all of these guys. So I think, and on the other hand, yeah, I think it's probably easy. That's basically the proof that it's unique. Yeah. Hmm. So no, an important subcase of this is when X is the whole space, right? Because then what I'm doing is I'm returning a reduced subscheme structure on the same underlying set as my scheme. So no, an important special case. Um, X equals Y. And you'll see this called X red or Y red. I mean, in fact, right, you're going to, it isn't quite phrased this way, but on your homework, you're supposed to show that if I look at Y and I look at the nilpotent elements of the structure sheaf, that gives me a quasi-coherent ideal sheaf. I didn't actually say ideal sheaf, but you could easily add that into the things you're supposed to prove on the homework. And so this is the closed subscheme that corresponds to that ideal sheaf. I mean, nilpotent's always going to the maximal ideal. Yeah, exactly. Yeah, right. If I require this at every point, then that's just saying that I'm nilpotent. All right, cool. Okay, need a bit. So it's always it's tough when creating this stuff to know like which stuff in Buckule I can skip and which stuff is important. But here's one that I've been hoping to get to fiber products today, but it doesn't look like we will. Um, so there's another really important kind of subscheme, which has the really catchy name of effective Cartier divisor. So an effective Cartier divisor is a subscheme such that on an subscheme X such that an open cover. This is actually going to be important. Not any open cover, some open cover by affines UI X intersect UI. So this is a closed subscheme of UI is the vanishing set of some TI. So what does that mean? That means that it's isomorphic to stack of O of Y on UI. I'm maintaining my X is the subscheme, Y is the bigger scheme, mod the ideal generated by this TI. So now whenever I write V of an ideal, I mean subscheme defined by that ideal sheaf. I'm specifying not just what points are in that vanishing set, I'm telling you the subscheme structure on it by telling you the ideal. For Ti not a zero divisor. Okay, so this is kind of weird. The way you should think about this, and kind of bad to say this because we still haven't talked about dimension yet, but you should think about this as meaning that it has codimension 1 everywhere. Right, so by the Kroll principal ideal theorem, this ring has Zariski has Kroll dimension 1 less than the Kroll dimension of this guy. So I think of this as I have some big scheme, and I have something locally always looks like the zero set of a function. So maybe it has multiple components, maybe it's sort of not reduced, maybe it's sort of thickened along some of these components. But if I look at a little neighborhood around my point, it just looks like the vanishing set of one function. Yeah.
I guess it's gonna be like, so here you say so it's gonna just become
No. I mean, it's a closed subscheme. I mean, this definition manifestly makes it closed. But worth commenting that this definition, right? This is by definition a closed subscheme. And something whose intersection with every open and an open cover is closed in that open is closed. Okay. Cool. So once we talk about dimension, this will be sort of a way of thinking about dimension 1 things. Now, an important notion that will get used later is kind of iterating this process. Iterate. So if I iterate, what does that mean? That means that I take x1 and y to be an effective Cartier divisor. And then I can look at x2 inside x1, an effective Cartier divisor there. Now, what does that mean ring theoretically? And of course, I can keep going, right? This means that, well, I took this quotient. So if my x is stack of some ring A, right, then x1 is v of t1, t1 not a zero divisor. And one thing I sort of said it here, but I want to emphasize this a little more. On affine schemes, there can be effective Cartier divisors, which you need to choose a non-trivial open cover to realize them this way. Right? So there are silly examples like z adjoins square root of -5. Right? So the maximal ideal 2 comma 1 plus square root of -5 defines an effective Cartier divisor here. As the maximal ideal, it defines a subscheme. That subscheme corresponds to 1 point. If I pull out the prime, let's say 2 here or 3, if I pull out the prime 3 here, this becomes a principal ideal. So there's an open cover where this is a principal, but it's not principal for the whole ring. So I want to emphasize here this sort of spec of A, I might have to keep shrinking. But in some neighborhood around a point, it has to look like this. So x2, what am I doing? I'm looking at v of t1, t2. So t wasn't a zero divisor in A. What do I need for x2 to be an effective Cartier divisor inside x1? I need that x2 is not a zero divisor in A mod t1. And then if I were going to put an x3 here, I would want an x3 is v of t1, t2, t3. And I want t3 to not be a zero divisor in A mod t1, comma t2. Okay, so this so this is an operation, an algebraic notion, right? Let me go back here. Mm-hmm. You mean this point of intersection? Well, I mean, if it were really I had a two-dimensional scheme here, and then one-dimensional scheme here, I don't know, maybe not. I don't think it's guaranteed, but I don't think it's guaranteed to not be. Yeah. Right. If I look at xy, that's not a zero divisor, right? And then I could look at x plus y, and that's not a zero divisor, and that cuts out the point where they intersect. And this is not a zero divisor mod xy. Right? So I couldn't put x or y here; those would be zero divisors. All right, cool. So definition, T1 up through Tk in a ring A is a regular sequence. Ci is not a zero divisor in a mod T1 through Ck. Oh yeah, sorry, Ti minus. So this is exactly saying that when I look at the zero set of Ti inside the zero set of these guys, it defines an effective Cartier divisor. So kind of at each point, I'm kind of uniformly dropping a dimension. I'm basically out of time, but let me get to the most important points with this. So it's sort of a nice property of a subscheme to be defined by a regular sequence. So we say that X is a regular subscheme in a neighborhood of each point of X, X intersect that neighborhood is equal to the vanishing set of a regular sequence. All right, so the sort of important, the algebraic way you'll usually think about this is, well, if I want to know something about some neighborhood of X, but I don't care which one, then I should look at the local ring at that point, right? And inside here, there's a maximal ideal. And since I'm in the subscheme defined by these guys T1 up through Tn, define a regular sequence, are all elements of this ideal. And I want that they define a regular sequence. Do, do, do. I mean, there's always this issue of not, what if your scheme wasn't connected? So I could say of codimension, and then I would be fixing what my n was. But I don't know, probably in theory, you might want to leave yourself open to the possibility that you have multiple components that have different dimensions. Yes, but sort of locally around each point, right? So it says that near a point, you can choose a small enough open set where you can do that. But again, because of this point about like there exist non-principal ideals that are locally principal at every point, right? If I take a non-principal ideal in here that's maximal, when I localize it locally at every point, it's still principal. The localization is a DVR. So, somehow like here, right, I would be saying like, oh, when I look at the local ring at that point, then the maximal ideal is principal, and that's giving me my regular sequence. And I'll just note, because it's an important term, a complete intersection is a subscheme where we can do this globally. Is a regular intersection. So this would again be of codimension, some fixed codimension, and it's a regular intersection of n effective Cartier divisors. So Vakil comments that it would be tempting to call this locally complete intersection, but that name got stuck on something else. So I'll get there. All right. Are there any questions? Then I guess we're out of time and should quit for the day. Yeah.
restriction of we're gonna function in space.
Mhm. You mean here?
Yeah.
I mean, that's when you say like, oh, just restrict a function from the ambient space, you're taking the reduced subscheme structure. Mhm. Yeah, but polynomial rings are Jacobson. I mean, nothing, it doesn't tell you anything for varieties. For general, I mean, right, it's sort of, yeah. Um, right, the kind of thing you should think about if you want to think about non-Jacobson examples is like local rings, right? So this is telling you like, if you take the local ring at a point in affine space, right, then there are, prime ideals in there that correspond to like irreducible closed subsets passing through that point, right? And you have an ideal that expresses, are you zero generically on that subset, which like you can't test by looking at the value at closed points because there's only one closed point. It's a local ring. So is that the kind of thing you're asking? Right? So that, the local ring of that subvariety is a quotient of the local ring of the bigger thing. And you can think of that as a subscheme of spec of the local ring. I think that's the kind of thing you're looking for, right? And there's a reduced subscheme structure on that guy, or you could have a non-reduced subscheme structure on it. Mm-hmm. Mm-hmm. Uh, in terms of like invertible modules, yes, right. Um, so I mean, you're thinking of the class ring. I mean, the being an effective Cartier divisor means that the ideal sheaf vanishing there is invertible, right? Because I'm telling you that it's locally a principal ideal. Principal ideal is free of rank one as a module over the ring. So I'm telling you that if I take one of these, the sort of correspondence you're looking for is if I take one of these effective Cartier divisors and I look at its vanishing ideal, that's an invertible sheaf. Um, and um, right, somehow like it was kind of a horrible name for the subscheme because usually like what people would actually be thinking about, like a Cartier divisor, that really means like the sheaf that is defined by the vanishing. Um, and so the effective part means that it's only things that are vanishing somewhere. Being a general Cartier divisor would also be like, oh, on this subspace, I'm going to have some poles.